Lucas Skatikowska Gino. I am a MSc student of postgraduate program in electrical engineer from Universidade Federal de Minas Gerais, UFMG. I will present the paper Optimization Technique for Efficiency Improvement in Visible Light Communication System. Andrea Cicciarelli is my advisor. Davis William de Lima Monteiro is my co-advisor. So what is VLC? VLC, Visible Light Communications, is a technology in which information is shared in free space by using light emitted in the visible spectrum 430 terahertz to 790 terahertz. VLC systems are best suited for indoor communications and have been extensively considered as a promising complement to radio frequency communication, RF. What are the advantages of VLC system over RF, considering the growing demand for data traffic? VLC operates over a wider license-free transmission bandwidth, which is the most important advantage. VLC presents greater immunity to electromagnetic interference and higher data security at physical layer. Some optical sources for both lighting and data transmitters propose. And in this context, we know that indoor environments can feature complex geometries and topologies, and we have a trade-off between system performance and power cost efficiency. In this paper, we propose a first implementation of an optimization strategy for indoor VLC transmission system based on genetic algorithm, in which, given the data rate and number of the optical transmitters and the target bit error rate, the optimization algorithm determines the optical system configuration in order to deliver the required signal-to-noise ratio, minimizing at the same time the required total emitted power. And here we have our scenario. An empty room with walls, floor, and ceiling at right angles has been considered. Initially, there are three transmitters on the ceiling, and the receiver plane is located 0.85 meters above the floor, corresponding approximately to the height of the desk. The dimensions of the room are 5 by 5 by 3 meters. And also, we considering a second scenario with 4 transmitters for comparison. This proof of concept does not include reflections. Therefore, only line of sight transmissions is considered. Here, this figure represents the geometry model. We have the psi angle of incidence, the phi angle of irradiance, f of v, field of view, and the d, the distance between the transmitter and the receiver. And considering an indoor optical wireless channel with Lambertian transmission model, the DC gain LLS can be modeled according to this formula. Here we have the parameters, the optical area of the photodetector and the Lambertian model number, which depends the theta, which is the same angle at half illuminance. And the other parameter we see the d, the distance, psi and phi, and g is the concentrator gain, in ts the optical filter gain. Ts and g are both assumed equal to 1 in this work, with no loss of generality. And the received power can be calculated from the transmitter power these equations. And considering an OOK NRZ modulation scheme, the bit error rate is estimated as this equation, where Q is the Q function. We estimated bit error rate from the SNR and at the receiver, which for indoor optical wireless system is given by these equations here. N0, the electrical noise power, was limited to the contribution of thermal noise variance, assuming the use of common pin photodetector and considering the relatively low power levels at the receiver, which allows to neglect the shot noise contribution. And here we have the parameters used in VLC system under study. We assume a low noise pin-FET transimpedance receive stage. So we define the optimization problem as give the number of optical transmitters directly modulated with OOK NRZ sequence at data rate of 200 megabits per second. The best placement of the transmitter on the ceiling has to be determined in order to minimize the required emitted power to ensure the bit error rate less or equal 10 to minus 6 in a circular area with diameter 5 meters. This circle was considered to avoid large valleys in bit error R in center of the room. This just to guarantee a bare on corners. So, but this corner have little chance to have its receiver. Even that, using FEC, we could still guarantee communication. More specifically, we have the objective function as this equation, power transmitter, which depends the power received and the DC gain, where the transmitter power depends on SNR, thermal noise variance, and the photodetector responsivity, in which SNR depends on the square of the inverse Q function, guaranteeing a bare less than 10 to minus 6. Here is the circle we consider. Basically, genetic algorithms have the initialization of a population and a parent selection, normally based on fitness functions. In these parents, recombination and mutation operation apply generation and offspring, and then survivors are selected based on the fitness function. Here, we have the definitions of genetic algorithm, and basically we use the gray code with 10 bits to representations, the recombination 1 cut point per variable, the mutation the bit flip, a population size of 100, and the stop conjunction 10,000 iterations. And the genetic algorithm converges to the optimal distribution, capable to ensure the desired target bit error rate in the specific region. Minimize at the same time the total emitted power, optical power from LEDs. For the first scenario with 3 transmitters, there is the evolution of each transmitter's power throughout the iterations. We achieve a power per per LED of 2.62 watts. And here, this figure shows the optimal distribution for 3 transmitters. A symmetrical distribution can be not here of the transmitters. And this figure below shows the respective SNR and BER distribution. And the SNR, the range between 10 and 20 dBs. And for the second scenario, with 4 transmitters, there is the evolution of each transmitter's powers throughout the iterations. Consider the minimal and mean of this power. We achieve a power per LED of 1.71 watts. And this figure shows the final distribution for 4 transmitters. Again, asymmetrical distribution of the transmitters can be noticed. And here, this figure shows the respective SNR and BER distribution. It can be noticed that the distribution becomes more uniform for 4 transmitters. And our conclusions, it can be observed that increasing the number of LEDs, the SNR distribution become more uniform. And when using 3 transmitters, the minimal emitted power per LED was 2.62 watts, giving a total optical power of 7.86 watts. With 4 transmitters, it can possible to achieve a power per LED value of 1.71 and with a total power of 6.84 watts. And the distribution of LED lights in a room, as well the correct choice of the number of LEDs, can lead to significant gains in energy efficiency, while still ensuring effective communications. Thank you.